on the penumbra of chemistry. Vanadium lingers, an element whose character shifts with the quiet movement of electrons. A subtle change in charge. A violet becomes green, a green becomes blue, a blue becomes yellow. Each oxidation state stands apart, distinct in its own form. Yet vanadium is not confined to single identities. Hundreds of mixed oxides exist, where phases overlap and merge, producing substances with properties unlike either parent. It is a lesson in balance and transformation. In this Venn diagram, each circle contains one oxide: vanadium pentoxide, vanadium dioxide, and V2O3. The overlaps show real intermediate oxides V6O13, V4O7, V3O5, etc., and how the metal-insulator transition shifts, broadens, or disappears depending on the mixture. We are talking about vanadium. Vanadium is famous for having several oxidation states with distinct colors. Red fluorovanadinite, found in the oxidized zone of lead-bearing deposits. This is rare. Another rare vanadium crystal is this one, found in India, called carbonsite, usually found as it is here, surrounded by steelite. Carbonsite is a calcium vanadium silicate hydrate. Here I am making a nicotine vanadium complex. I start with 0.6 grams of vanadium sulfate, and I mix this with some nicotine in a acidic methanol solution. If I were to guess, I would say that in an acidic medium, the vanadium cation will be coordinated with several methanol ligands. In one place there will be a VO bond, and around the equatorial plane will be solvent ligands. Think of a square pyramid. With the vanadium cation solvated by methanol, our nicotine molecule can then coordinate with this pyramid using the nitrogen on its pyridine to displace the methanol ligands. The pyrrolidine nitrogen is protonated and won't coordinate. Then I centrifuge down the solid precipitate. The sulfate is most likely just the counterion, and the reason it turns a darker blue, there is less available water for it. Similar to the copper tetraamine. Different environmental conditions lead to thermodynamically favorable outcomes. The x-axis is the pH, and the y-axis being the concentration of the solution. The pH and the concentration are what can tune redox potential. Into a beaker, those with access to dilute sulfuric acid, they can pour. For those fortunate enough to have 98% is exothermic, meaning that a lot of heat is released. Not only does sulfuric acid easily dissolve in water, but being strong diprotic acid, it has protons ready to give away its hydrogens to the surrounding water molecules. In a proton transfer equilibrium, hydronium ions H3O plus and bisulfate ions HSO4 minus and sulfate SO4 minus. Now we are ready to add our vanadium in the form of sodium or ammonium metavanadate. This is vanadium in its +5 oxidation state, and the solution should appear yellow. Finally, you will want your reducing agent. Powdered zinc metal. Zinc is powerful enough to reduce vanadium 5+ all the way through vanadium 4+, 3+, which appear blue and green respectively, all the way to vanadium 2+, which is violet. Many reducing agents don't do this. So zinc is important. Sulfuric acid is also important, as hydrochloric acid won't work, and many other acids are not strong enough, or they chelate, or they do something you don't want. So it needs to be sulfuric acid, and it needs to be zinc powder. Anyway, vanadium in +2, if you get there, is a strong oxidizer, meaning it will not stay as a +2 for very long, as it will find something to oxidize, bringing itself back to +3 and +4.